Welcome, dear students, to your lesson 6 on functions, and here we are going to do the logarithms. Actually, it's just yet an easy function that we do here in grade 12. So let's get started with the function. So to get started, I thought it would be fine, or it would be nice to actually draw a graph of these logarithms and to find out where they are actually coming from. Well, since we are very comfortable with our exponential graphs at this point, I thought it fit to start with an exponential graph. So we are going to have a graph of y is equal to 2 to the power of x here. That's the one that I am using. So notice that is going to be gx in this situation. So we are working with gx actually, and gx happens to be 2 raised to the power of x. So normally, I would fill this table when you're available, but I thought for time purposes, let's rather do it like this. So if you substitute minus 2 in place of x in that function, you should definitely get 1/4 as indicated over here. If you say 2 to the power negative 1, you get a half, and you carry on. You definitely, if you say 2 to the power 0, you get 1, 2 to the power 1, you get 2, and 2 squared, you get 4. So that's how you get the coordinates to plot. So we are going to actually plot the graph that we already know. That is the graph of y is equal to 2 to the power of x is the exponential graph. So if you are looking here on the board, I already have my graphs, but let's see if we can plot negative 2 and 1/4. I think you're agreeing with me that it will be over there, and then negative 1 1/2, it will be over here. So the points are already here. 0 and 1 is that coordinate. Well, this one is particularly highlighted, 1 and 2, and then of course 2 and 4 will be somewhat, so we're going to just put 4 up there and 2 is over here, so let's just assume it's over there. Well, you're noticing that if you join those points that I just drew over there, you would definitely get the exponential function, which is the function that you're already seeing here. So this is the exponential function we already know. 2 to the power of x. As you are seeing, it's actually an increasing function, and it has this y-intercept as 0, 1. Those are the things you want to keep in mind about the exponential function. And don't forget, the x-axis happens to be the asymptote of that function. Remember, we talked about when the base, so at this point, the base is actually 2, so we are talking about when the base is greater than 1 in this situation. So as you can see, our base is 2 this time around. So what we are going to do is to reflect this graph in the line y is equal to x. And remember, if you are reflecting in the line y is equal to x, what happens is that your x becomes your y, and your y becomes your x. Okay, so generally the rule says if you have xy, the image itself will have yx. That is all there is to it. So what is it that I'm going to do to get the other graph here? That is a reflection of the exponential graph in the line y is equal to x. Well, I'm going to take this table right here on top, and I am going to interchange y with x, so we can get the table down here. You're noticing that 1/4 was y here. Now I put it as the x value. So I just interchanged the x and the y values, and therefore we have this table over here that is formed as a result of that. So if we sketch a graph that passes through these points down here, we will be sketching a graph of a reflection of 2 to the power x in the line y is equal to x. So why don't we go ahead and see if I plotted that one right? Well, notice if I go to 1/4 and negative 2, that would be this point over here. It's very easy to find, especially if the graph is already there. So half and negative 1, it's at that point, and 1 and 0 definitely is that point. And then 2 and 1, x is 2, y is equal to 1. It's particularly highlighted. And 4 and 2, so our x of 4 will be over there. So 2 is somewhat that high, so I'm going to put that point over there. As you can see, we will have a graph which is also an increasing function, like we are noticing it's already here on the board. Well, that would be the reflection of the graph y is equal to 2 to the power x in the line y is equal to x. Well, but from what we know now, if we are reflecting in the line y is equal to x, we'll be getting the inverse function. So in other words, the inverse function of an exponential graph happens to be this graph over here. Maybe you're wondering, what is that graph exactly? From what we know, let me create a bit of space. From what we know, here is what we actually know. Okay, there is a bit of space provided for us. We said that if we would like to find the inverse of a function, firstly, you write down the equation. So we want to find the equation of the inverse of that. And then the next thing is you swap x and y. So your x is going to be 2 to the power of y now. The last step is you make y subject. And there you realize that it's not very easy to take y from where it is and make it subject to the formula. That is why we are going to introduce something called the logarithm and just see if you will understand this definition here. However, I'll explain it a bit further. So from what we have here, the logarithm of a number is the exponent to which a base must be raised to produce the number. I know it just sounds like words, so let's rather explain what this is about. So let me have a bit of space here so we can just first of all explain that before we go too far away. Okay, so what I normally like to do is I write things that are true, such as 9 is equal to 3 squared, or write 32 is equal to 2 to the power of 5. Those are the things that we already know. What about 25? Let me again write it as 5 squared. Well, what will happen if I want to write these as logarithms and the correct logarithms that will work with these exponents? Notice you may take your calculator and check. What you do is you leave the base as a base. The exponent this time is what will become subject to the formula. That is what this definition is saying. You will understand it just now. So your 2 will become subject to the formula, and then you introduce this function, which is the logarithm, and then the base will stay the base, and the base here is 3. Everything else should fall right into place. So this statement right here is a very correct statement. And then let's try this one again. The exponent here is 5. That's the one that will become subject to the formula. And then you say log, and the base here is 2. So you still let it be the base. Like that. That will be a correct statement to write. Try this one. Let's hear. I'm sure you're saying 2 is equal to log to base 5 of 25. So please people, whenever you have, say for example, you want to write 100 as 10 squared, when you write this as a log, you don't actually show the base, especially the base of 10. We don't really expect you to do so. So your 2 this time, instead of writing it as log to base 10 of 100, we actually do not expect to see the base there. If you just write log of 100, we understand that you mean to base 10. So now, if you understand how I was moving from this side and going to that side, and if you have checked with your calculator that these things that I just said are accurate, so we will go back to where we were just a second ago. We didn't do this to enjoy our lives. We want to get the inverse of this function. So now, remember, we were stuck at x is equal to 2 raised to the power y, and we wanted to make y subject. I just gave you a rule that will help you to make y subject, and I said you introduce the logarithm, so you're going to say y is equal to log, and you keep the base. The base is still 2 of x. So please people, what we just finished drawing up there is the graph of log to base 2 of x, this one. If that red graph is 2 to the power of x, like we have already indicated, this blue one will be the graph of log to base 2 of x. Now, Please, this is exactly how the logarithm graph looks like. Please take care of to notice these points. If there is a coordinate which is 1, 2 on the exponential, it will be 2, 1 on the logarithm. If we have 0 and 1 on the exponent, it will be 1 and 0 on the logarithm. It's that simple to notice. And notice, if the base is greater than 1, both the graphs of the function and even the inverse will be increasing functions. Well, that's enough for this one. Let me show you the basic rules that we know now about a logarithm that has a base greater than 1. Well, we already have your notes here. I made sure you have all of them. So you're seeing that if your base is greater than 1, your functions are going to be increasing. So let's put a few more things. Here I prefer we keep it as b, the base. Let me just say b to the power of x here as well. So we have consistency, okay? So we just finished plotting itself, the graph of the logarithms to the left-hand side. So now let's know a few things about these graphs. Well, the one thing is for sure, you are noticing that the x-axis was, let's talk about the exponential function. Let's write the domain of the exponential function this side. Well, if you are looking at it, the exponential function, which is this one right here, it can go all the way to the left the way it wants, and it can go all the way to the right. So all the values of x are included here for the domain. We just have to find a way of writing that properly. Okay, so x is an element of real numbers. This is for the exponential function, right, for this function. This is what I'm talking about. So now let's go for the range of that same function. So I'm going to force the range to fit here. The range is going to be y is an element of real numbers, but look at the exponential function. Do you see that the x-axis, it will not even touch the x-axis here. This will be your asymptote right here. So the x-axis is the equation of y is equal to 0 right there. That is the equation thereof, and that is the asymptote for this one. So y can be anything else above 0 and just not 0 or smaller. So here your y is an element of real numbers, and your actual range should be written as y should be greater than 0, not even equal to. That's for the exponential function. I want you to appreciate what will happen now for the, you see the inverse function, which is the logarithm. So you can see it over here. Well, I already have your notes here. I hope you are seeing them. Look at how we write the domain. You can see that this graph, the blue graph, can go all the way down, which means all the y values at the bottom can be included, and all the y values above, as you can see, this graph carries on. So y is an element of real numbers is the proper way of just talking about the range of that function. But when it comes to the domain, that is the x values that we include, we are seeing that we have a limitation here. We have to consider that vertical asymptote right here, this one. We are not supposed to touch it, especially if we are dealing with a logarithm graph. So we always have to be to the right of that one. So when we say something like that, we say x is greater than 0 at all times for logarithm functions. So you can write it as this, or if you are that person, you can write it as between 0 and infinity. Just don't include any of the two. You cannot include 0 because it's an asymptote, and we do not include infinity because we don't ever get to infinity. Well, if you are looking at these two things, you can see that the domain of this one was x is an element of real numbers. If you just interchange x with y here, it will become y is an element of real numbers. As you can see, the domain of the exponential function happens to be the range of the logarithm function. And again, the range, look at this one. Let me write this one properly. X is an element of real numbers. I like this way. I like this format rather than this one. So this is the domain, isn't it, of the logarithm graph. So notice, look at the range. the one in green, this one. If I were to just remove y and put x where y is, I'll come up with this domain here. So that's all you have to do here. Remember, these things just interchange. If you were able to give us the domain and range of the exponential function, just know that you have to interchange them to get the domain and range for the inverse function, which will be the logarithm function. So it's very simple to see. I hope you are seeing this. Okay, perfect. Now that you know the domain and range of these functions, let's go to when the base is a fraction. What happens then if the base is a fraction? Well, I didn't draw this one in advance, so I hope you're going to be here to actually enjoy doing this with me. So let's put a scale properly here. We need to have, I'm going to just have a scale -1, -2, and let's have 1 and 2 this side. How high did we go? We went all the way to 4. I need 4 on the other side. So I'm going to just make sure, let's do this a bit fast. Okay, and then on the y, I am going to also need a maximum of 4. Hope I have enough space. So let's go 1, 2, 3. I can extend this one a bit. Let's then have 4 up there. Okay. I don't really need -4, but I do need -2, so I'm going to put it over here. Okay, so now let's sketch this as fast as we can. Please, people, at this point, maybe you're wondering which function we are actually sketching. I decided to let us do y is equal to 1/2 to the power of x. So let me put it somewhere where it's not on the way. So y is equal to 1/2 to the power of x here. That is what we are solving for. 1/2 at 2. Oh my. Okay. Firstly, it will look like that, 1/2 to the power of x. So if you substitute -2 in that equation, you will be sure to get 4. And if you substitute -1, you get 2. 1/2 to the power -1 will be 2. 1/2 to the power 0, you get 1. And 1/2 to the power 1, it will be 1/2, and 1/2 squared will be 1/4. So that's how you get those y values that are there. Let's sketch them quickly. I think you find it easy to sketch. -2 and 4. -2 and 4, it's up here, the highest I can go. And then -1 and 2, so I'm over here now. And then 0 and 1, right there. 1 and 1/2, so I should be somewhat halfway. And then 2 and 1/4, somewhat half of 1/2. So this is the graph that we have. Let's just hope we are going to be able to join all those points. It's going to be a lot of work for me. I missed the last one. All right, so I should never touch the asymptote. It does look like we managed to touch our asymptote this side here. Okay, let me try again a bit harder this time. All right, so from what we have here, this will be the graph. It carries on, you know. It carries on and it carries on in that direction. This will be the graph of y is equal to 2 to the power, rather 1/2 to the power of x. Would you say it's an increasing or a decreasing function? Well, I'm pretty sure you're noticing that this one will be a decreasing function. At this point, we are dealing with a base when the base is actually in between 0 and 1. So here, whenever the base is in between 0 and 1, we will have a decreasing function, as we have noticed. Well, what do we do now if we would like to have a function and we would like to have the inverse function? Well, we already know that we are supposed to reflect in the line y is equal to x, but it will be a lot easier if we can actually put on a table. Let's see if we can have a new table for this. I hope that will not be a problem. Let's see. was thinking it may do that. Okay, just a minute. There we go. So now after the table is here, now I would like for us to interchange, you see, the coordinates of this table so we can be able to draw the inverse function of this function that is on the board, the exponential function. So all I need to do is to go ahead and do something of this sort. Let's have the x and y for this one here. Let's see what to do here. So I just have to write the y values. Remember there were 4, and then there was a 2, and then there was 1, then there was a half. I'm copying the y values in place of x. That's all I'm doing. And then the x values, I'll copy them in place of y. And then that's -1 there, and then there is 0, and then there is 1 and 2. That's all there is to it. Now let's sketch them. Let's go ahead and sketch this one. So let's find 4 and -2. That would be a coordinate over here, all the way here. Let's put it somewhat there. And then there is 2 and -1. So somewhere here. And then 1 and 0 over there. Then half, a half is x, and then 1. So, interesting. I'm going to just try hard here. It should be, let's see if that coordinate, what was it? 1 and a half and 1. Let's see. Right here, a half and 1. I'm going to put it over there. And then we have, let's have 1/4 and 2. A 1/4 and 2 somewhere over there. So as we can see, we are seeing exactly the shape of this function. So it is going to be a decreasing function, definitely. It's just we have to be careful so we can pass through all the points. There we go. This is what we have right here. And it's a logarithm function as well. So now we have a basic idea of how the logarithm functions should look, but maybe you're wondering which logarithm function is it? Well, if we started off with y is equal to a half to the power of x, the first thing we do is we swap. So your x is now going to be equal to a half to the power of y, and then to get the equation of the inverse, it is now going to just be log, and then you maintain the base, and then you put x over there. So the equation of this one would be log to base of a half of x. So people, if this is a function right here, this definitely will become its inverse right there. And don't forget, these two are reflections of each other. They are symmetrical about the line y is equal to x, like that. That is where your line y is equal to x would be. They are reflections of each other in that line. So as you can see, when the base is between 0 and 1, both the functions are decreasing function. But when it comes to the domain and range, it's exactly the same. Look at the blue graph. You can see that there is not even a single point in time when it actually touches the y-axis. It's always to the right of the y-axis, which means for this one, x has to always be greater than 0. And the range is y is an element of real numbers for this one all the time. So as you can see, this will be the shape of logarithm functions, like the blue graph, if the base is between 0 and 1. And if the base is greater than 1, you look right here on the left-hand side. These ones will be increasing function. So just like how you remember the graphs of your parabola, the basic graphs of when the a is positive and the a is negative, you should also remember the shapes of these graphs over here. So now that we have an idea of how these shapes look like, let's make some basic statements about the logarithm graph that we can use all the time. Okay, so here, like I said, if your base is between 0 and 1, so for consistency, I'm going to change this one to b to the power of x, and then this one log to base b. So we are talking about the base here. When the base is between 0 and 1, we can safely say all the time these things will be decreasing unless if they've been reflected somehow, but if it has been, there were no transformations done to the graph, it should be a decreasing function, just like what we are noticing. And if ever someone asks us to write the domain of the logarithm function, which is right here, I would just quickly say x is an element of real numbers, and as you can see, there is that asymptote here, which is the y-axis, so x has got to always be greater than 0. And then the range for the log graph is y is an element of real numbers. Okay, let's write it like that. So that is all you need to remember about the logarithm graphs. You should know the shape, and you should be able to know where your asymptotes are, your domain, your range, and your intercepts. You see, the logarithm graphs pass through the 0.10, and then this one passes through 0.01. It's very simple to remember, really. Okay, so feel free to get these things right whenever you're asked to draw or to sketch these log graphs. It should be very simple for you to do. Well, now that you have all the information with you, let's see what else you can learn about these logarithm functions. Well, let's see if you can reflect them a bit, So at this point, I'm going to say, if you wanted to sketch a graph of y is equal to log to base 3 of x, I'm assuming that you should know the shape thereof. It should be an increasing function. Like I said, you should remember the shape, and the shape was something of this sort. So let's say I draw a graph of log to base 3 of x. Let's say this is the one to base 3 of x. That's the function. Well, let's not forget the critical points. It passes through a point 1 and 0. Well, and remember, this is the y-axis, this is the x-axis. Well, the beauty of this is that you can find coordinates on this graph by thinking about the inverse of this graph. So if you're asked to draw one more point on this graph, you have to think of the function y is equal to 3 to the power of x in your head. And then you perhaps just give one x value here. Say, for example, you say when x is equal to 1, what is the y value? 3 to the power 1, that will be 3. So you know that this coordinate will exist on the inverse function, which will be something of this sort. But then, what will this same coordinate be when it goes to the inverse function? Well, you should be able to write it as 3 and 1. So that, let's say there is that point, you should be able to put at least one more point when you sketch these graphs. Okay, so this was just me drawing this graph right here. Don't worry about it. The exponential graph is not needed. So let me actually remove it once and for all. We don't need it. I just needed it for explanation purposes. Now I have the logarithm graph log to base 3. What will happen then if someone asks me to reflect this graph now in the y-axis? Where will the image be? Well, I think you are noticing that the image, if we are reflecting in the y-axis, we have to go to the left. So this part here, let me just reflect it the way I'm seeing it. This part should just simply be like this. On the other side, you are reflecting it, aren't you? And then this part will just somewhat carry on like that. So what I want to emphasize is that this point, which was 1, 0, when it comes this side, it should definitely be -1 and 0. And then this point that was 3 and 1, when it comes to this side, it will be -3 and 1. The y values are not changing. What is changing are the x values. So the rule says if you reflect in the y-axis, your point xy becomes -xy. In other words, x becomes negative. But if x becomes negative, normally they will ask you to find the equation of this reflected graph. So normally they'll say, well, this is your function of x, and then there is, after you reflect it, then there will be a function called hx. Now, how will you get hx? Well, you first of all start with the equation that you had. You see, you had log to base 3 of x. What you do is you just go ahead and make x negative. So in this situation, you just write y is equal to log to base 3 of -x. So that will be the function of hx right there. It will be log to base 3 of -x. You just leave it like that. Well, as you can see at this point, this graph right here, what's inside, remember I said here inside that part, you should only have something greater than 0 inside that. So we are seeing that x is already coming as negative x. One may wonder then, what will be the domain of the blue graph? By looking at it, you can see that it will be x is an element of real numbers, but x is all the time smaller than 0. So the x values we are using here should simply be smaller than 0. That will be the correct domain for the reflected graph. Y is an element of real numbers. It remains the range of both these graphs that are on the board. On the other side, the domain of this one is x is an element of real numbers, and x is all the time greater than 0. You can see where the graph is and how to get the respective equation, can't you? Well, I'm hoping we maintain the same attitude as we reflect in the x-axis now. So if you are reflecting in the x-axis, the story becomes a little bit different. So let's go ahead and draw the same graph. Remember, we were working with log to base 3 of x, so I'm going to draw the graph of log to base 3 of x as we remember the shape. Now, since we already have one or two coordinates that we know are on that graph, let's put them. We know this one, you should know it off by heart. We explained how we got 3 and 1, so I'm just going to put 3 and 1 right there. Well, this time around, I want to reflect this particular graph right here, the logarithm graph. I want to reflect it in the x-axis. Now, let's reflect it together. Well, if you are looking this part here, this part down here, this which goes all the way down and as close to the y-axis as possible, it will go as close to the y-axis as possible, but on the other side. This is what will happen. And then that part will come something of this sort. So I have managed to reflect that graph in the y-axis, rather in the x-axis, as we are noticing. So as we do that, we will have that purple-like graph. Now, the drag is in trying to find the equation of that one, but I think if you're looking at the purple graph properly, you will notice that it's the shape of the other type of logarithm functions. Well, if you are still remembering, let me just remind you, if you check your left-hand side, check right here, look at this graph that's over there. That is the graph that I said is the graph of the logarithm function if your base is between 0 and 1. That is, if your function, or if your base is a fraction rather. So in this situation, the graph that we've got, it resembles that particular graph. So what do we do in that situation? Well, I'm going to do it in two ways. I'm going to do it by just looking at the graph first. By looking at that graph, you can tell that the base for this particular graph should be a fraction. So when you write it, you don't have any other fraction to write. If this is a 3 over here, this definitely has got to be 1/3. So that will be the equation of this other graph, log to base 1/3 of x. That is just by looking. But there is also a method you use if you know your logarithm laws. So we may say, whenever we are reflecting in the x-axis, look at the rule, what will become negative is y. If you're looking at these coordinates, I couldn't change 1 and 0 because it's still at that same point, but if you look at 3 and 1, when it comes to this side, it will now become 1 and negative 3. You can see that it is the y value that changes its sign. So if your original function was y is equal to log to base 3 of x, the second function that you write, which is, we can call it gx now. Let's call this one gx, and this one is still function of x, right? The original one. So if you want to find the equation of gx, which is a reflection of function of x in the x-axis, you go ahead and make y negative. So you make that one negative, and you have log to base 3 of x. Well, from what we know, you have to make y subject, and when you make y subject, this is what happens. The negative comes there, and then it will be something of this sort. So those that remember or that know their log laws, there is a law that allows us to take that -1 all the way up like this, and it will become x to the power -1. Well, when it does that, there is again another law. No, here this is not a log law. Let's write it like this. I can just write that one as 1 over x. Those are exponents themselves. Well, then this is a trick we use in logarithms. Whenever you have, here it's a fraction and you want to change it to just x, so you have to come and change the base into a fraction. So you come and you write log to 1 base 1/3, and then it will be log to base 1/3 of x. So as you can see, you will get to the equation anyway, but this is using the log laws, which most of you, if you're doing caps at this point in time, you may not actually have to bother doing those log laws. But here is one thing I want you to remember. If you reflect in the x-axis, it's y that becomes negative. And if you reflect in the y-axis, it is x that becomes negative. So remember these ones for your reflections, please. You already know that if you reflect in the line y is equal to x, you will be getting the inverse of the function. So that part you already know. Let's add a few more to this. Well, now that we know what we do know at this point, I think it's about time we just sketch a few graphs and just get the inverse and see how it looks like. So let's just sketch a bit before we solve these equations that I put up for you. So I'm going to just sketch these questions here, A, B, C, D. So if you want to just sketch them in advance, go ahead, and then you see how I will sketch them myself. Well, we created enough space for it, so I'm going to go ahead and sketch the first one. So we have A, and it's 5 to the power of x. At this point, now that we know, we don't waste too much time. If we know the shapes, it's just better that way. I just thought let's practice like this to check if you're understanding what I mean. So 5 to the power of x, from what we know, it should be an increasing function, and it's an exponential function. It should look like this, very steep as well. So it should pass through 0 and 1. Like that. That's 5 to the power of x. Perfect. Normally, I prefer you put at least one coordinate. And since at this point we are running out of coordinates to put, let's put, say, when x is 1, y will be equal to 5. Because if we play around and try to work with 25, we may regret it later when we fail to get enough space for it. Well, we were asked to draw the function and also the inverse. Well, to draw the inverse of this, you just have to reflect in the line y is equal to x. We already know the shapes of this graph. That's why I said just know the shape of these graphs. It will also be an increasing function, and it will look something of this sort, I hope. Let me see if I got it right this time. I hope so. Okay, good. So here, this is the correct graph for the logarithm, and this coordinate, you see it was 0, 1 here. At this point, it will be 1, 0. And this graph here, if that is 5 to the power x, this one here will be log to base 5 of x. So that will be the inverse right there. Well, you want to show at least one coordinate. There should be another coordinate, and that point will be 5 and 1. You see how I just interchanged the two? As easy as that. So that's how you answer A. I think you answered it correctly. I doubt there is any problem with that. So feel free to get stuff like this right. So let's go and do B. In fact, I feel I shouldn't do everything. There is no need, really. So, however, let's do it fast instead. 1/5. So it should be a decreasing function. The moment you pick up the base as a fraction, you are dealing with the exponential function, which is decreasing. And that is the function right there. Y is equal to 1/5 to the power of x. And then maybe you may want a few coordinates. Well, that one is already a known one, 0 and 1. Maybe if you put -1. At -1, x should be, y should be 1/5 to the power -1. That should be 5. Okay, so we have that coordinate 0 and 1. That's a 0 and 1, and then we have 1 and 5. So this is the function f. Now, if you have forgotten how we do it, to get the inverse, we just say if we have y is equal to 1/5 to the power of x. If you're still wondering what I'm doing, you first of all swap. If they ask you to get the inverse, swap them, and then make y subject. You introduce the logarithm, which will be log to base 1/5 of x in this situation. Okay? So that's how you do that step of finding the inverse. So let's sketch the inverse. The inverse function will also just be a graph that is decreasing. And at this point, this is when knowing the shapes of these graphs will work. So it will be a decreasing function that is something of this sort according to what we learned. In fact, I was just reflecting in the line y is equal to x over. This line should cut exactly there when they intersect. If you put it at a different place, you are not going to get your marks for sketching these graphs at all. So please make it a point that you do that right. So this is the log to base 1/5 of x right there. Well, do you still feel I should do C? Maybe we must. I think it's going to be the last one I do, though. I'm not going to do D. You can do that one on your own, and I'm sure you'll be correct, whichever. So C, here are our graphs. Log to base 4 of x. We remember the logarithm function. There it is, log to base 4 of x. So I have this function, and it's passing through 1 and 0. So at this point, it is actually a little bit difficult, to try get the inverse of this one. But now that we have the common knowledge that if it's a logarithm, the inverse should be a function. So if this is log to base 4 of x, definitely the inverse should be 4 to the power of x. And that is an easy graph to draw because it just looks something of this sort. So just reflect it as well. It will just be helpful to actually reflect the one that's available. So this will be y is equal to 4 raised to the power of x, and this point is at 0, 1. As you can see, the domain and range of these ones are exactly as I've discussed a few minutes ago. They have not changed at all. So this is how you sketch these graphs, and it's very simple to get them really. Maybe you are wondering, how do you move from y is equal to log to base 4 of x until you get to 4 to the power of x? So maybe the first thing you do is to interchange. So your x is now log to base 4 of y. And then what do we remember? The exponent becomes the subject of the formula. So in this situation, x should be the exponent. So it will be 4, which is the base, and then you raise it to the power of x is equal to y. Remember, we will do this thing just a few minutes from now when we do equations. So that's precisely what I was hoping you would know about these functions. That's easy really to do. I know you are able to do that one. Okay, let's answer a few equations so you can see what I meant just now. I want you to be able to solve equations as well. So here I have just 3 equations, just so you can get used to them on how to solve it. Remember, if we have a question such as that one, when you have log and it is 1/4, it is 1/4 here, and x is equal to -2. At this point, I'm answering this one over here. So as you are seeing, I said to you, here, let's just perhaps move 2 steps back. When we introduced logarithms, we had x is equal to 2 to the power of y, and we were stuck here. So I said, you know what, it's the logarithm that can take it down, and then the base will remain the base, which is still 2, and x. So if you still remember this operation that we did, you should be able to easily solve these ones, because I'll be asking you now to move from here back to there. You should be able to move from exponential to logarithm and from logarithm to exponential. The idea is just take the base and remember whatever is subject of the formula was the exponent before. Notice the exponent is what will become the subject of the formula. So it means -2 must have been up here for starters. And then you then take the number that side. So it's very simple to notice, isn't it? So at this point, if you have 1/4 raised to the power -2, it's as good as you have 4 squared. So we are going to say this is 16. Okay, that's how you solve it. So if you have this one over here, let's call it our number 2. Just go to the left-hand side a bit. As you can see, the base is still x here. The subject of the formula is 2, so that will be equal to 49. So if you look at it, I just have to find something that we square to get 49. That would be 7. As you can see, your x would be 7 in this situation. Because the exponents are the same, the x value should, the bases should also be the same. Well, let's do this one as our number 3. I like the way it looks. You see, I explained before that if you have something of this sort, you should know, since they are raised to the power of the same number, the laws of exponents have helped us to notice that if we have a over b raised to the power of n, is the same as saying a to the power n and b to the power of n. This we already know. So how can we use this information to solve what we have? Well, because we are actually moving from this side back to that side, not the other way around. So that expression can now be written as 28 over 7, all raised to the power of x. And then when you divide your 28 with your 7, you will simply find that you get a 4 over there. So let me do this. So you have 4 raised to the power of x is equal to 10. Now you want to get x. At this point, you cannot change 10 to a base of 4 at any point. So you have to go ahead and say x, make the exponent subject to the formula, and then the base is 4. So we are going to put 4 at the bottom of 10. So you need to just do the log to base 4 of 10, and that should give you some 1.66 as our solution for this one. So that's all you need to know about these equations as well. It's very simple, won't you say? So let me wind this up and show you a few inequalities, some of the things you are expected to do in examination type questions. So let's go ahead and do those ones quickly. That one we did already. Okay, so before we go there, let me just see if you are fine with the domain, how to find the domain. If the function of x is not just log x, if they give you some other logarithm other than log x, so then what you do is you just take whatever is there. Just know that whatever that is should be greater than 0. So if you want the domain of that, all you need to do is to say 3x minus 1 should be greater than 0. You will be able to easily find the domain of that one. So notice, and I'm sure everyone can see how this is supposed to be, just x is greater than 1/3. Of course, you write your x as an element of real numbers as well. Well, look at this one. You target whatever is inside the brackets. Whatever that is should be greater than 0. If ever the logarithm is going to work, whatever is in place of x should be greater than 0. So I have to put, or maybe I should do this. I wanted to put 5x to the other side, but on second thought, let me do it this way so I can teach you a bit more. Now you're noticing you have to divide by -5. So the sign will change. So this will be 3 over 5 now. So this will be the domain you get. All right. So now we're going to do these worked examples that are more examination type questions. So this is exactly how they ask you logarithms in exams. It's very easy, really. For example, here you were given log to base a of x. It's passing through points 16 and 2. From what we know, if we have an expression such as this one, and we can see we have an unknown, which is x. All we really need is one coordinate. If we have one unknown, we need one coordinate, so we can substitute it. In place of y, you're going to put 2. And in place of x, you can simply put, what is that one? Is that 16? Yes. So let's put a here and put 16 here. As you can see, I will be expected to move away from logarithms to exponents. So you take the base will always be a base. The subject of the formula will go back to being an exponent, and that will be 16. So what is it that you square so you can get 16? Well, that would be 4 squared. you can go ahead and say plus or minus 4 square root, but as for a base of something, remember we said it can never be negative. So that is why here we will take a of 4 as the correct answer over here. Well, it means we were dealing with an equation which says log to base 4 of x. If someone asks us for the inverse, we are going to let them know that the first thing they have to do, you see that's b. That's b right here. Let me answer b. The first thing they have to do is to swap the 2, and then after that you make y subject. So how do you make y subject? You're going to say the base is still the base, and the subject of the formula goes back to being the exponent. And this right here will be the inverse. So we're just going to write it like that as the question asked. That will be the inverse of the logarithm graph. Okay, let's go to those inequalities. I can't wait to finish the inequalities because that's where the problems may come. You see, it's the same question. It's just that now there is a little k here. We already know that our k should be 4 if we are moving, if we have 16 and 2 here. So please notice if we solve it just like how we solved this one, we will figure out that our k is equal to 4 here. There's no need to do it again. It's the same graph passing through that same point, 16 and 2. So what is it that I want you to do here? Well, maybe you're wondering, how do they use these logarithm graphs to get things going? Well, before I answer that, let me just ask you to give me the coordinate of this q here. I'm pretty sure everyone is saying 1 and 0. So there are such questions as find a place, let me just show you the question, I have it here. Use the graph to solve for x if function of x is smaller than or equal to 2. That's what I want to talk about for a minute. You want to solve for when this graph is smaller than or equal to 2. How do you do this? Please, people, don't forget this is as good as you're solving for y is smaller than or equal to 2. So you go to a place where y is actually equal to 2 on the graph. And yes, you're right, it is exactly right here. Y itself is equal to 2 at that point on that function. So at that point, which is point P right here, we can see that y is equal to 2. So we would like to find our root for this inequality right here. And the x value that is here will become the root. So we know that our answer should have x and it should have 16 one way or the other. We just don't know whether we should be greater than 16 or smaller than 16. So what we do is you ask yourself, if this is the line which says y is equal to 2, do you want to go above the line or below the line? From what we are gathering, when we say smaller than or equal to, we have to go below the line that we are talking about. So we want the part of that function which is below that graph. And everyone can tell that this is this part of the function. It is below the line y is equal to 2. So as you are noticing, that function is going to the left of 16, isn't it? So if it is going to the left, this is the part of the function that we want, is to the left of 16, meaning it's smaller than 16. Well, the question is including, so we also have to include 16. That was going to be our solution if we didn't have an asymptote. But if we leave it at that, and there is this y-axis, which is the asymptote here, we will get everything, we'll get some marks wrong. Because if you say x is smaller than 16, you are including even the values that are negative. But you can see that your graph is never actually cutting the y-axis at all. So as you can see, you have to appreciate, you have to take it into consideration that this graph cannot touch 0. So it should be, x should be smaller than 16 but greater than 0. So it should be like this, between 0 and 16. Even if the question is including at this point, it's greater than or equal to, you cannot include the asymptote at this point. So you just write smaller than. Rather, x is greater than 0. X is between 0 and 16. So these are very good type of questions. You should master them to be able to get your answers right. So because it's a very important skill, let me have 2 more graphs to work out on this same thing and see if we can easily get these things going. So look at what we've got here. We have the graph of log to base 3. I think you can easily sketch that one now. Log to base 3 of x. Let me just do it quickly. That would be the correct shape of the graph of log to base 3 of x. Right? Well, perfect. That's function of x. Here it is. Maybe to feel good about ourselves, we may put 2 coordinates. That one, 1, 0. So what you're doing is you're thinking of a graph of 3 to the power of x right now, and you are finding out what's what. Notice, however, where we are going. Do you see that we have to solve that when there is a 2 somewhere? So x there is 2, so we would like to figure out what will happen in the exponential graph. So put the x value of 2. They're going to give you a y value of 2 at one point. So put it as an x value this side. If you have an x value of 2, what is 3 squared? I think you're noticing it will be 9. So this coordinate right here will be the coordinate of this graph. So how will it be like when it comes to the log graph? Well, it will be 9 and 2. You just invert it like that. So just as you did there. Perfect. Now I managed to draw the graph of function of x. So drawing the graph of gx is not going to be a big problem because it's just saying gx is equal to 2. So that should be some horizontal line that is passing through that point at 2 right there. They are cutting each other at that point. So this is the function or gx, this one. So what is the question now asking us to do? We have to solve this. In other words, when is function of x smaller than or equal to gx? That's the question. So you want to figure out when function of x is below gx. So find the time when the black graph is below the blue graph. I think you are noticing exactly what to do. So you go to a place where they are exactly equal, that is when they are intersecting, or just go to a place when y, you see, remember you're solving for log to base 3 of x is smaller than or equal to 2. So go to a place when it is equal to 2 and you will see that is that point. The x value there is 9. You just do not know whether you should be greater than 9 or smaller than 9, but you can easily pick up the root is 9 to work with. Well, from what we are gathering, the black graph is below the blue graph to the left of 9. It comes back this way. So as you are seeing, it's to the left of 9, so it means it's smaller than 9. And like I said before, if you are coming this way, watch out, there is an asymptote here. You want to appreciate it here at x is equal to 0. So you have to mention that it should be greater than 0. You can include 9, that's sorted. Okay, that is a very good skill. Like I said already, let's have more. One more sum. One more. Maybe 2 more. Oh, this one is interesting because it has got a straight line. So I hope we're going to enjoy this. The graph of log to base 4. Oh, are they no long? You see, this is how the graph of the logarithm looks like. It's very simple to draw. Let's put the y-axis and the x-axis here quickly. So I have my 1 and 0 here. And since it's log, this graph is the graph of log to base 4 of x. I just need a few coordinates, you see, I'll have 4 to the power x in my head. So if I put x of 1, I'll have 1 and 4. It means when it comes to this side, it will be some 4 and 1 coordinate. Let's just put somewhat here, over there, like that. So that's one more coordinate on that function. This is function of x. Now we would like to draw that straight line, gx minus 2x plus 2. The first thing you try and do is to get the x-intercept by putting y of 0. So you are noticing that 2x is going to be equal to 2. It means your x is equal to 1. So this graph will have an x-intercept right here. The y-intercept is already at 2, so we are sorted with that one. So that function is going to be something of this sort. I just have to really learn how to pass through all points. That's not very straight, but that's the best we can do with the time we have. So this one right here happens to be gx. So the question is asking, when is function of x, from what we are gathering up there, log to base 4 of x, that's function of x, isn't it? When is the black graph below, that's smaller than or equal to, the red graph? When? So this one should be above, and this one is the one that is below at this point. So find that time. So what you have to do is to first of all go to when they are exactly equal. When these two functions are equal, go to their point of intersection, and you're noticing it's over here. So this is where it starts. So it starts right here. You know that 1 is an important value, so you know that we're going to have to play around with x and 1 somewhat, somehow. We just don't know whether we should go to the right of 1 or to the left of 1. So now think again. When is the function of x, which is the black graph, below the red graph? I think you're noticing it is this side of that. You're seeing the red graph is above, isn't it? It's here, it's above the x-axis, while this one is actually below the x-axis. So that is to the left of 1. Well, if we are going to the left, we are headed towards the y-axis. So the moment we are headed towards the y-axis, we want to acknowledge that we can never pass that point. So I think I've given you enough of these ones that look like this. So why don't you answer this one so I can let you be for now? I think answer this one so I will be convinced that you know what you're doing. Okay, if you're done with it, well done. Let's draw the graph of log to base half of x together. It will look something of this sort. It's very interesting when you know the shapes of these graphs. So let me put 1, 0 here. That's the y-axis, that's the x-axis, and this is the graph of log to base a half of x. It has got to be a decreasing function. Well, let me think of one coordinate I can put. So I'll be thinking of half to the power x in my head. So if I think of maybe -1, I know if I put -1, I'll get 2. And again, if I put maybe -2, I will get 4. So I can interchange these coordinates, whichever one I feel like. So I'm seeing that putting 2 and -1 may work. So I'm going to put 2 and -1 here, and maybe over there put 4 and -2. You see, all I had to do was to interchange these coordinates that I got from thinking of that one, which is the inverse. Okay, perfect. This is a half, by the way. Now, what do I want to do? I want to draw the sketch of gx, which is x minus 1. It has to pass through this point, which is -1, according to me. Wow, look at my scale. Okay, so that's where -1 is. And the x-intercept, if you put 0 here, you'll notice the x-intercept is also at 1. So that graph is actually an increasing function. It's passing through these 2 points, like that. So this is gx, if you did it correctly, and this one here is your function of x. So now here is what I am asking you. You are being asked to solve for when, again, function of x is greater than or equal to gx. So when is it that they are equal? Firstly, you go to their point of intersection, and again, that is right here. So you know that x and 1 will play a very good role. So now you're thinking, should I go to the right of 1 or to the left? Well, you can see that the black graph is only above the red graph when we go to the left. You are seeing how it is above, isn't it, when this one is going down. So it is actually to the left, and once you are approaching the left side, don't forget to acknowledge the y-axis. I think you get the point. Okay, so thank you very much for watching this video. That is all I wanted to share with you about the logarithms. Please get very good at them. They are very easy functions, so enjoy everything. Thank you.